Hello, this is a structured approach to modifying successful heuristics by Doctors Simon Martin, Matthew Craven, and John Woodward. The overview of our position paper. Sorensen in 2015 argued that there were too many essentially identical algorithms. He was particularly looking at papers and heuristics based on with analogies from nature, such as, I don't know, bee swarms, insect swarms of various types, that kind of thing. And he was essentially arguing that they were done without any mathematical rigor. So you take some analogy and then say, just because there's some analogy from nature, therefore it must be some kind of optimization problem, and off we can go. And he was saying, really speaking, you need to look at the mathematics behind it to understand what it is we're really trying to do. We've been looking at this, and we've been looking at the origins of all of this stuff. And we've been looking at the Cook-Levin theorem, for example. And so we will focus on algorithms to solve problems, because we want to make the point that a heuristic solving a problem is working on an algorithm, because the definition of a problem that is in MP, one of our hard problems, is a problem that is defined algorithmically. And we use reductions. Now, reductions go back to Turing, but in this case, we're looking at CARP reductions, and we show not only do they preserve complexity, but they also preserve structure too. And the idea is that if we properly analyze a problem as an integer problem, so an objective function and constraints, then we can look at constraint families, looking at Trevisan, who defined constraint families. And then we can look at gadgets as tools for mapping the constraints from one problem to another. In some cases, it's easy to transfer successful heuristics between problems, especially if the problems are dual or equivalent. But is it possible to find other mappings between heuristics using other techniques? And that's what we're doing in this position paper. We're exploring this possibility and showing that there might be some future work in here. So let's look at what we're doing here. We're saying that if you take a problem such as, I don't know, vertex cover, and use some gadget which modifies the constraints, it refines the constraints with Hamiltonian circuit. Maybe we can use some clever heuristic, which is good for say, Hamiltonian circuit. Say Lin-Königin, because Lin-Königin is good at Hamiltonian circuit, TSP, that kind of thing. Could we modify the Lin-Königin algorithm, which is very effective for TSP, and use it to solve vertex cover? That's the general idea. Now, so let's look at Cook-Levin. Cook-Levin said that our problem in MP is a problem that is only solvable by a polynomial time algorithm that runs on a non-deterministic Turing machine. They show how you can implement any algorithm on a non-deterministic Turing machine as a Boolean formula. And so, since any problem can be encoded as a Boolean formula, any algorithm can thus be encoded as a Boolean formula. And so the real point is that we're talking about algorithms, and the problems are really defined as algorithms. They're not problems in their own right, they're problems as algorithms. This is important because it allows us to then modify it with different heuristics and focus on what's going on. So if any problem can be represented, or most, because problems can be represented as an integer program with an objective function and a bunch of constraints, it's the constraints that really define the problem. So we can look at constraint families, where it's essentially a common language which allow us to show how some problems are refinements of other problems. Trevisan in his 2000 paper goes on to design constraint functions and constraint families on which gadgets can act in terms of integer programs. And a constraint function is simply a Boolean function. A constraint family is a set of constraint functions, And a constraint then is just an assignment to that constraint function. So we'll look at that in a bit of detail. So we have identified some problems that fit into a constraint family, which we will call allocation, where an algorithm works on the vertices in a graph. Here's an example of an allocation problem. Okay, so this is vertex cover. And what we're saying here is we've got this vertex here and this vertex here covering this graph. Now, it's a very simple graph. In fact, it's not NP hard because it's too simple, but it's a good example of a reduction. And anyway, we don't care about, and we're not talking about complexity here. We're talking about structure preserving reductions. So a simple example just shows you how it works. You could cover this graph by AB, BC, or AC. In this case, we're using AC. And the reduction that maps between, that turns this graph into a Hamiltonian circuit is one where you treat each route between each edge as a circuit, and you do this by this approach. And we do it using edge gadgets. An edge gadget is essentially a one-way street. Now you've got the situation where you've got some edges where one is in the cover and one is not. That would be the situation of AB in our graph. Or you've got the situation where both are in the cover, that's AC. So you need to have a graph, an algorithm which turns this into a digraph, because essentially we're going to make a route round here. We're going to go round here in a route, visiting all of the edges. How is this done? Well, this little switch here is edge gadget, says that you can either, in the case of AB, just go down here and you've covered all the vertices, or if you need to do this situation, you can go down there. So you can go down there, up there, down there, and down there. Sorry, no, that's not right. Let's do that. You go like this, down there, up there, down there, up there, there, and you've covered all of the street, if you like, all of the vertices when you started at one end and come at the other end, and these essentially go here, and they force the whole thing to be a route. Imagine the situation that you're in a town where at the end of every street there must be a pub. Okay, so there's going to be some situations where you have this situation as a pub just at the end of one street, and you're going to have the situation where there's a pub at the end of both streets just because of the layout of the town. Your job is to start at position A and visit all of the pubs and get back to A again, having just been everywhere once. Okay, so you are doing a vertex cover that is also a Hamiltonian circuit, and that's essentially what this is about. If we look at the constraints, let me just clear my pictures. If we look at the constraints, this is the integer program for vertex cover. And this is the number one here is the essential constraint. It is saying that an edge can be of one of the two types. If one of the vertices in the edge is in the cover, then it'll be 1. If both are in, it's going to be greater than 1, but it can't be 0. If you're in the cover, one of them's got to be in. And this is Hamiltonian circuit. Now, what's going to happen is this constraint is going to be modified by the gadget onto this constraint. This constraint says you can go from A to B, or you can go from B to A. And what this is doing is saying that we're modifying this gadget so that if both are in the cover, you can go from A to B and then B to A. That'll be the situation in our pub crawl where you've gone to a particular pub and you've gone down the street one end and met a pub at the other end. And you've gone around the town and you might have to go back to that pub again, but then you go down the other side of the street back round. And then that way you are able to go around the whole town, visiting every street once, but you're only doing every vertex once as well. That's the idea. So here's an example of algorithm how we might do a vertex cover using Lin-Kernighan. Now, I'm not saying this is more efficient. I'm just saying that there is an algorithm that could do this. The problem then becomes to find a tour that is also a vertex cover. So we'll use an adjacency matrix of the graph as a bit mask to let us know whether we are legal or not illegal in our routes. And we use the Lin-Kernighan to find a route with respect to the bitmap. The simplest way is just to, the simplest answer would be just to find a route around the town and then just cover every other vertex, because in a circuit, every vertex has degree 2, and essentially that's what you're doing. You're smoothing out the vertices which are with more than 2, using the gadget to just make it vertices of degree 2. But that's not really very good, because you won't get an efficient vertex cover. So what we can do is we can take every vertex, every edge, and we can choose which is the vertex which has got the greatest degree, and then you can do 1 over the degree, and that will give a cost value to the edge, and then you can use that with the objective function of Lin-Kernighan, and that will tend to find those vertices which have got higher degree, which are going to be the ones which are going to be the most useful in any vertex cover anyway. And then finally, you can verify the result by just running a simple algorithm over at the end, which just sees whether the edges that you've found are touch every the vertices you've found touch every edge in the graph. That'll run at order n. So the conclusion. Cook says, concentrate on algorithms for solving problems, not the problems themselves. We can represent them as integer programs, and as such, we can then look at constraint families and the potential gadgets between the gadgets. And we can identify constraints and the heuristics working on these constraints and see if they can be modified. And in that way, we can design modified heuristics and meta-heuristics. And our future work is to work on this, and we will test on this using this particular algorithm that I've described, but we're also going to look at other constraint families. For example, we've come up with another one, which is about partitioning graphs. So we're going to look at graph coloring and vertex cover, and so we can do mappings between those. Thanks very much.